So we're looking at functions, and more importantly now we want to look at what the picture of the function looks like, the graph. So things to keep in mind when sketching. So once we've collected data, maybe we've performed some sort of experiment or something like that, and we want to see if a relationship exists. So by plotting that data and looking at the picture, then we can see a pattern more easily. Does it lie in a straight line? Does it lie exponentially? Those sorts of things. So the type of pattern is determined by the shape of the data. If you look at it and you see that it looks like a known function, fantastic. Because then we can come up with a function and we can then make predictions using that data by plugging into the function it appears to be. Now, when we are plotting our graphs, important things to keep in mind, your scale of course needs to be consistent. So whatever you choose to be a size of a unit, it's got to stay that way all along the axes. Of course you can have a different scale on different axes. There's no reason why the scale on the x-axis has to be the same as the y-axis. The only issue with something like that is, I guess if the relationship was a circle, that could be a problem, because if you don't have the same axis, it's not going to look like a circle, it'll look more like an ellipse. So known functions can easily be sketched from key pieces of data. Y-intercepts, we know that happens when x is equal to 0. 0 is always an easy number to substitute in. X-intercepts, similarly, when y equals 0. Once you've got the intercepts, if you know the basic shape, then the curve's pretty easy to sketch. If you're unsure, just plot a few more points. So in that idea going way back to year 7 or whatever it was when you first were doing this, of drawing a table of values. Well, you don't have to physically draw the table of values, but that idea of picking specific points to get a feel for what the graph's doing. Then certain graphs have specific features, like our hyperbola we know has an asymptote, things like that. As I was just saying, so if in doubt, use that table of values idea and plot extra points until you get a feel for what the curve is doing. So let's start with the most basic of all graphs, our linear function. And there, I guess, is the most basic linear function, y equals x. Now, if you plot your data and you get a straight line, then you know that there's going to be a direct variation between the two pieces of data. So it'll always equal, y is equal to some constant times x. As I say, it's called the linear function. Now, as you probably realise, when you are doing experiments with data, it might not lie exactly on a straight line because you do get, errors in readings. So sometimes a line of best fit will suffice to approximate a linear function. But all straight lines can be transformed from this basic straight line of y equals x. We can shift it up, we can shift it down, we can shift it across, we can rotate it, we can reflect it, we can do a combination of all three. Just in case you don't recognise it when you see the equation, how do I recognise that the function is indeed a linear function? Is it in this form? Y equals mx plus b. So again, really to break it down, hey, notice the power of y is 1, and on the other side, the power of x is 1. That's an indication, hey, I could well have a straight line here. So the terms contain at most one variable, so you don't see x times y in a straight line. It's usually just one variable, and all those variables are to the power of 1. And when expressed with the dependent variable as the subject, so y, we know that the coefficient of x turns out to be the slope of the graph, and b turns out to be the y-intercept. I hope it's been explained to you at some point, but this is why we plot y on the vertical axis and x on the horizontal axis. Because when you are drawing graphs, you should always put the independent variable on the horizontal axis and the dependent variable on the vertical axis. And that should be the same in all graphs you've been drawing in science. So if you were drawing a displacement time graph, time would be on the horizontal axis and displacement would be on the vertical axis. There are some special straight lines, and there's the ones that, if we got ones that are parallel to the x-axis, we know they will always have an equation y equals some constant value. So this one here would be y equals 2. And similarly, ones that are parallel to the y-axis will always be x equals some constant number, and if it was going through the same point there, that would be x equals 3. So there's two special cases of straight lines. So we get a question like this: show that 2, 4 lies on the line x plus y equals 6. And so we go, okay, well, let's actually have a look at that. I've mentioned this before, but the advantage with a show that question, you can simply substitute in and go, hey, what do you know? It works. So it's not like we physically have to try and find an equation line and all this. We can sub it in. And hey, look at that, 2 plus 4 is 6. What do you know? So yes, that does lie on the line. All right, so that's the first bit of theory for today.